All right, let's talk about something that feels like it's pulled straight from a sci-fi movie, but is actually happening right now. We're going to decode quantum computing, a technology that's getting closer and closer to changing, well, pretty much everything.
Okay, so to really get this, we have to start with the basics. Every computer you've ever used, from your laptop to your phone, works with bits. You can think of a bit like a light switch. It's either on or it's off, a 1 or a 0. Simple. But a quantum computer, it uses a qubit. Now, a qubit is more like a dimmer switch. It's not just on or off. It can be on, off, and a whole range of values in between, all at the exact same time.
And look, this isn't just a small upgrade, you know? It's a completely different way of thinking about computation. We're stepping away from the nice, neat rules we're used to and diving headfirst into the weird, wonderful, and frankly, mind-bending world of quantum mechanics.
So what's the big deal with this qubit? Well, because a classical bit can only store a single value, that 1 or that 0, a qubit holds this whole spectrum of possibilities at once. It's not just one answer, it's the probability of all the possible answers all wrapped up together. And that's what unlocks these incredible quantum effects.
So, these qubits have a couple of main, what I like to call, superpowers that classical bits just don't have. And this is where we really start to take all that strangeness from quantum physics and turn it into a real advantage. The first superpower is called superposition. The best way to think about it is like a spinning coin. While it's spinning in the air, is it heads or tails? Well, it's neither. It's kind of both, right? It's in a state of potential. A qubit is just like that. It's in a superposition of both 0 and 1. But the moment you look at it or measure it, boom, the spinning coin lands, the superposition collapses, and the qubit is forced to pick a side. It becomes a definite 0 or a 1.
Okay, if you thought that was weird, get ready for the second superpower, entanglement. This is the one that Einstein himself called spooky action at a distance. Imagine you have two gloves, a left and a right, and you put them in two separate sealed boxes. You mail one box to the other side of the world. The moment you open your box and see a left-handed glove, you know instantly that the other box contains the right-handed one. Entangled qubits are linked just like that. Their fates are tied together, and it doesn't matter if they're a millimeter apart or light years apart.
So you might be thinking, okay, that's all very strange and fascinating, but so what? How do these mind-bending concepts from physics actually help a computer do, computer stuff? How does spooky action actually solve a problem?
Well, it turns out that these quantum properties allow for a whole new type of algorithm. And we're not just talking about making things a little bit faster. We are talking about creating algorithms that can solve certain problems that are, for all practical purposes, completely impossible for even the fastest supercomputers we have today.
This brings us to a concept called quantum parallelism. See, a classical computer is like a detective who has to interview every suspect one by one. It takes a long time. A quantum computer, because its qubits are in superposition, can basically explore every possibility at the same time. It's like interviewing all the suspects at once in a single step.
And the most famous example of this, the one people call the killer app for quantum computing, is Shor's algorithm. It's designed to do one thing really, really well: find the prime factors of gigantic numbers. Now, for a classical computer, that is one of the hardest problems imaginable. In fact, pretty much all of our modern online security is built on the fact that it's so hard.
Just look at the difference here. The scale of the speedup is it's hard to even wrap your head around. A problem that would take the world's most powerful supercomputer billions of years, literally longer than the age of the universe, a quantum computer could theoretically solve in a few hours. That's not an improvement, that's a whole new ballgame.
So why does this matter to you? Because all the digital locks that protect your bank account, your emails, your private data, they're all based on this one problem being too hard to solve. Shor's algorithm holds the key that could one day break all of those locks. It's exactly why there's a huge, urgent race to develop new kinds of encryption that even a quantum computer can't crack.
And it's not just about breaking codes. Quantum computing is definitely not a one-trick pony. There's another famous one called Grover's algorithm. This one gives you a massive speed-up for searching through giant, messy databases. This could totally revolutionize fields like data science, logistics, even drug discovery, just by making it way, way faster to find that needle in a haystack.
So, if this technology is so powerful and so revolutionary, why don't we all have quantum laptops sitting on our desks? Well, as you can probably guess, actually controlling this weird quantum world is incredibly difficult. It's a huge engineering challenge. The single biggest problem is that qubits are unbelievably fragile. The slightest little vibration, the tiniest change in temperature, can knock them out of their special quantum state. It's a process called decoherence, and it basically ruins the calculation. So building systems to correct these errors without destroying the information is a massive hurdle. But the potential rewards are just as massive. We're talking about designing new medicines by simulating molecules perfectly, creating revolutionary materials we've never even dreamed of, or building a new generation of artificial intelligence. That's the prize everyone is chasing.
And really, when you boil it all down, the entire field is about this one thing. It's the art of taking these bizarre, almost unbelievable rules of the quantum world and being clever enough to harness them, to turn them into tools that can solve some of humanity's most difficult problems.
So here's the final thought I want to leave you with. Quantum computing isn't about making your video games load faster. It's about building an entirely new kind of computer to solve a whole new class of problems. The digital world we live in was built on the foundation of problems that we thought were unsolvable. This technology forces us to ask a pretty profound question. What happens when they're not?